introduced the divisors on curves for several things. We have the divisors associated to rational functions, which are the principal divisors. We have divisors associated to polynomials in the ambient space, and now we want to introduce one other set of divisors, which are the canonical divisors, which are associated to differential forms. So this is slightly more close to analysis or something in feeling. So let's talk about canonical divisors, but not so much, because we have an algebraic approach. So we want to introduce differential forms. And the corresponding divisors. But we do this in a completely algebraic and abstract setting. So my definition is the following, which will maybe look a little bit scary. See in a moment what it means. So let F be the vector space over the field of rational functions, which is generated by the following symbols. So with the basis and the symbols. So I write this df, so with a bracket around it, f in KC. So for every, so obviously the f should be the same, so this is small f. So this is a completely huge vector space. So for every rational function, we have a basis element. So it's so the dimension of the vector space, if you wish, is as big as the number of elements here. So it's an enormous vector space. Okay? Obviously, we don't want something as ridiculous as that. So we divide it, we take the quotient. So the KC vector space of differential forms on C is the quotient of this by a certain subvector space. By the following things. So I can generate it by the following thing. First you have, if I take whatever this is, d of the f of 2, d of the sum of two rational functions, this is supposed to be the sum. You know, we are in a vector space, it makes sense to talk about the sum. This is all for all f, g, and kc. Then we have first these relations. The second one, we have, if we take the product of two rational functions, take the corresponding class here. This is, so I should write it like this, minus. So I divide by the subvector space generated by this difference. Okay? And here, this is minus f dg minus g df. And finally, we have just dA for A and K, our ground. So we have this hugely infinite dimensional vector space we divide it by enormously many relations. No? For every number, if our rational function is a constant, then d, this class d of it, which I have here taken as a basis vector of the original vector space, is 0, and then I do this. So we have this huge vector space, we divide it by a huge subvector space, and obviously we have no idea how big the quotient might be. The quotient might still be huge, or it might be 0, or it might be anything in between. We can write this in a more kind of slightly less scary way, and I will do this note, so remark. We can reformulate this definition as follows. So a differential form on C, which is supposed to be which is an element of this vector space on C, is a finite linear combination I should maybe say here, I write df for the class of the df in bracket. So the opposite to what one usually does. So this df is an element in f, but here the df in brackets is an element in f, and its class in the quotient, the space of differential forms, yeah, I write them as omega c. And the corresponding thing is just df written like that. I mean, it's a bit. So, now I just want to translate this into something which looks slightly more reasonable. Namely, we see it's a finite linear combination sum I, fi, dgi, where fi and gi are rational functions. So this is a KC vector space by just multiplying by functions. So h times sum fi dgi is equal to sum I h fi dgi. And obviously the sum corresponds to the sum of the coefficients. And we have the relations d f plus g is equal to df plus dg, d of f times g is equal to f dg plus g df, and so this is for all f and g in KC, and d of a is equal to 0 for all a and k. So this is just a reformulation of this. If this df is now the class of the df in brackets, then the fact that this dfi form a basis means every element can be written as a linear combination of them with coefficients, these fi's. And if I go to the equivalence classes, this subspace I divide by will give rise to these relations for the elements. I just you see that the d of f times, so this difference is supposed to be 0, which means that this is this vector space. Now this is just a kind of slightly less scary way of writing the same thing. Still, it doesn't tell us anything about how big this vector space is. So we write, as I said, omega c for the C vector space of differential form. So you have also differential forms in differential geometry, but they somehow have a slightly simpler feel to them because one doesn't need to be able to deal with rational functions. So there are a few obvious things that we can see from these relations here. Namely, it's not very difficult to compute in simpler form the d f for certain f's. We can express them in. So I just have the following remark. So first, so these are all exercises. Well, maybe the first one isn't because I do it. So if h is equal to f divided by g, where f and g are elements in Kc, then obviously it follows that f can be written as g times h. And so I can apply the formula. So with that, thus it means that df is equal to h dg plus g dh. And so one can translate this back into a formula for dh. So it follows that dh, so I write it as df divided by g, is equal to a formula you are maybe some form familiar with, is 1 over g squared times gdf plus minus f dg, if I didn't get the sign wrong. So it's like the formula we learned for the derivative of fractions. So you get this as a consequence of the definition. If you want to see what d of a quotient of two functions is, it's this. And in a similar way, this maybe I leave as an exercise. You have kind of all the rules for derivatives. So if I take d of a times t to the n, where t is an element in Kc, so Kc, then you can easily compute that this is a times n times t to the n minus 1 times t, just using this definition. In the same way, if I have a polynomial in two variables, so you just that follows from the this rule you could call the Leibniz rule, and it follows from that by simple calculation. And in the same way, if f is a polynomial in two variables, and I take now two rational functions, so I could ask myself, what is the d, also the differential of f applied to these two rational functions? And you would expect to get some kind of chain rule, and that is what you get. You get this is df by dx, so usual partial derivative of this polynomial, evaluated at fg times df plus df by dy dg. And all this 2 and 3 are an exercise. It follows directly from the definitions that you just write this down as a polynomial, you apply these rules, you will get this result. So that you can see. Okay, so we want to use this. So now I told you that, so we have made this enormous vector space with these enormously many relations. So we have a priori no idea how big this finally this vector space omega c is. So Kc was written like this. So it could be, so it's a quotient of an infinite dimensional vector space by an infinite dimensional subspace. It could be infinite dimensional, it could be m, it could be 0, it could be anything in between. Now the claim is this is a one-dimensional vector space. So somehow precisely cancels out, and so this is subject of the following theorem, which I unfortunately cannot completely prove for lack of time, although it's not so difficult. So theorem. So omega c is a one-dimensional KC vector space. In fact, one can say a bit more. If T is a uniformizing parameter, at any point P and C, then T is a basis. Okay, as a vector space. So every element can be written in a unique way as a rational function times dt. So this is the first statement. The second statement is some regularity. So if now f is not just an element in Kc, but is regular at a point P, and T is a uniformizing parameter at the same point, then it follows I know I can write df as sum g times dt, because it's the basis, where g is a rational function in Kc, but under these assumptions this is also regular at P. So with g and furthermore, if f is also a uniformizing parameter, then this G will be a unit. So it means G of P is non-zero. Okay, so this is the statement. So you can see, so the claim is this enormous vector space divided by an enormous subspace is actually a one-dimensional vector space. I can choose the d of a uniformizing parameter as a basis, and if I do this, then for any function which is regular at P, also the coefficient will be regular at P, and if the coefficient is even a uniformizing if it was even a uniformizing parameter, then this thing will be a unit, so it will be non-zero. Okay, so this is, and you have to think of this as some kind of derivative. So basically, if you have a function which vanishes to first, if you have a function which is regular, then its derivative is regular too, and if the function vanishes to first order, then its derivative is does not vanish at the point. This is somehow what this corresponds to. So I will just give some kind of sketch of the proof. Actually, the sketch consists in the fact that I only prove a small part of this. I will prove to you that the dimension of this vector space is at most 1. It could still be that this vector space is just 0, but this I don't disprove. But I prove to you that the dimension of this vector space is smaller or equal to 1. It's either a one-dimensional vector space or it's 0. And then one has to make some more effort to prove the rest. And this, although it's not very difficult, but it will require a different approach, I do not prove this regularity. So let's try to do this. So this is the sketch. So by definition we know that omega c is a C vector space. So we want to show that the dimension as a KC vector space of omega c is smaller or equal to 1 by showing that for a uniformizing parameter at P, the vector space is generated by dt. So if T is a uniformizing parameter at the point P in C, then dt generates omega c as a C vector space. What I don't show is that dt is not 0. So let's just look at it. Maybe so maybe at first this is kind of, well, as a remark before. So T is a uniformizing parameter. So so the claim is, so now just if now let's do it more generally. If F is an element in Kc, which is algebraic over K, then it follows F is constant. Okay, so if I have an element which is algebraic over the ground field, then it's constant. That's I'm going to use in my argument, and that's quite simple. So if F was algebraic, then we have an equation sum I equals 0 to n, ai f to the I is equal to 0, where the ai are not all 0, and ai are some elements in K. We can evaluate this at any point in C. This gives that sum I equals 0 to n ai, which is always the same ai, f of p to the I is equal to 0. So this is, just, this is now a number. These are numbers. So a number in some, so I see this is an algebraic equation just in one variable for f of p, a polynomial of finite degree. This has finitely many solutions. So b1, so bn, which might be also equal. So, or maybe I write ps. So thus it follows that C is equal to the union from I equals 1 to S of the inverse image under F of bi. Now this F is a is a function. I mean, a rational function. But anyway, so where it's defined, it's zeros. So the inverse image of a point will be a closed set. So it means C is a finite union of closed subsets. So as C is irreducible, it follows there exists an I such that C is equal to F to the minus 1 of bi. And so it means F is constant. Okay, so now this was a side remark. Now we want to apply this to T. So we take our point. I take P a point in C, T a uniformizing parameter at C, at P. Then we know that T is not the constant function, because a uniformizing parameter, otherwise it would not be a uniformizing parameter because it would be constant, and so the derivative would be 0. So it follows that T is transcendental. Over K. And so as the transcendence degree, if I now take, let's now take any other function. Let f be an element in Kc. As the transcendence degree of Kc over K is 1, because it's a curve, it follows that f must be algebraic over Kt. As the transcendence degree of Kc over K is equal to 1. This means that C is a curve. It follows that f is algebraic over Kc, over K of T. No? The field extension generated by adding T to this. So that means thus we can write sum I equal, so sum I equals 0 to n, ai of t, f to the I will be equal to 0 in Kc. And so ai of t is just some rational function in T. So this is an element in Kt. And I can choose this n to be minimum, so the smallest degree. Minimal. So I take the smallest possible degree for this polynomial. Okay, and now we want to see what we can do with that. Now we can apply to this our the d. So we want to see that if we can show that df is a multiple of dt, then we are done. So let's compute df. So we just take d of this expression. So it follows that sum I equals 1. Well, maybe it should be 0. Yeah, 0. N the ai of t by dt how should I put it? Yeah, I mean you see here this really we know that also extends to rational functions, that this will just be, if we do this, I claim what I get here is this, that I take just the derivative of this. So this is a rational function in T. It's a small extension of the lemma we had before, of the exercise. We had before, if I have any polynomial, I just get the derivative. And I claim if I have a rational function, I just get the derivative times dt if I take, so this is the same as d of ai of t. I claim this is equal to this. And this follows directly. And this is, so this would be plus the thing when I apply to this should be 0, because this thing is 0, so the d of it is 0. So this means this is equal to sum I equals 0 to n ART I times f to the I minus 1 times df. No, this is just, if I take d of this expression, it will be the sum of these two, except obviously there's one difference. Or maybe I write it like this. So this would be what we have this, and so then maybe I don't write it again. This means that if I instead that this one is equal to minus this.
Shouldn't it be 0 if I is the sum? It's the first sum.
What?
If I.
Oh yeah, certainly. This is just so I can. Okay. Sorry, that was misprint. And then I just do this thing. Therefore, this is 0, so I can write this is equal to minus this. Okay? And then I can solve for df. That's not so very difficult. So df is equal, what is it? Sum I equals 0 to n d I of t by dt f to the I divided by sum I equals 0 to n ai of t times I to fi minus 1 dt. Okay, what? Well, there's a minus. And then finally, so this f, express the f in this form. Obviously, this only works if the denominator is not the 0 function. But the denominator cannot be the 0 function because this would mean that I have a relation of degree 1 less for f. So denominator is not 0. Otherwise, f satisfies an equation of degree n minus 1. And so we see that df is a multiple of dt, and this is true for every f, and these df, they form a basis, so it follows that there's only one generator. This dt is the unique generator. So it could still be that dt is 0, in which case we are out of luck, because obviously you cannot do anything with 0 equal to 0. But it turns out not to be the case. The theorem is it's a one-dimensional vector space generated by this dt. Okay, so this is the proof as far as it goes. Okay, so yeah, that's not very fast. So let me see. So now we can associate to such a differential. So we have a differential form we can associate to a divisor. No, because we are doing everything in terms of divisors. And the divisor of a differential form will be, we write it like this, where the t is a uniformizing parameter, and then we take always the multiplicity of the function written in front of it. So let me write this definition. So let omega, I write it omega, so this is a differential form which I don't take to be 0, be a differential form on C. So we define the divisor of omega. So how do we do this? So we have to define its multiplicity at every point. So let P, we point in C. So we can write by our theorem that omega is equal to f times dt with f an element in Kc. And f obviously, as a divisor, if it's not zero, it's a non-zero element in Kc. And so then we say the multiplicity at P of omega is defined to be the multiplicity of P of the coefficient f. And so we should notice by the part of the theorem I did not prove, this is well defined. So if say S is another, so I didn't tell you, so obviously dt, t is a uniformizing parameter, t, that's important, no? Where t is a uniformizing parameter at p, otherwise this definition doesn't make sense. So if S is another uniformizing parameter at P, then we can write, we know that S, which we wanted, maybe then S, then we know that ds is equal to u times dt, where u is a unit. This was the theorem, but the part of the theorem I didn't prove. And thus, I can write omega as f times u times dt. But as u is a unit, the multiplicity of this is the same. So that's known as nu p f times u. Okay. And so this multiplicity is independent of the choice of the uniformizing parameter. Okay, so this is well defined. So
you want over u ds or
what?
You want to write w as or omega?
Yeah. Okay. Yeah, if I write omega, this would be, say, f over u. Yes, and so it would be the same. 1 over u is also u. Okay, sorry. Okay, so the divisor of the differential form obviously is just, again, the sum of the points with multiplicities is the divisor of omega, which is defined to be, as before, the sum of all points in C, the multiplicity of omega times the point. It's always the same. So, such a divisor associated to a differential form is called a canonical divisor on C. So, divisor of a differential form C is called a canonical divisor. C, and obviously there might be more than one there is often more than one canonical. There's more than one canonical divisor because after all we can always multiply by rational function will change. But if one doesn't care which one writes Kc for the canonical divisor. So also we denote it by Kc like that. K like canonical, however, written in German. Okay. So I mean, obviously, the name canonical divisor somehow indicates that it's a very important divisor, which is canonically given to C, associated to C. So note, omega c is a one-dimensional vector space over the field of rational functions on C. Thus, for any element omega in omega c, we have that omega c can just be obtained, it's just all multiples of omega. So it's the set of all f omega with f in kc. No? I mean, every non-zero element. Obviously, if it's a one-dimensional vector space, any non-zero element will be a basis. So in particular, we needn't have taken any. And by definition, the divisor of f omega, if you just look at it, you have the coefficient is now f times omega, you apply the multiplicity is just additive. So it follows, by definition, the divisor of f omega is just the divisor of f plus the divisor of omega. No, because for every point p, the multiplicity at p is the multiplicity of f plus the multiplicity of omega. No, it's just that, so if I want to be compatible with this, maybe I call this function g, then it becomes nu p of g times f times u, so obviously nu p of f plus nu p of g. And for every point, this means that divisors f. So, therefore, we see that the canonical divisors form an equivalence class under linear equivalence. No? So they are all the divisors which are linear equivalent to one canonical divisor. Thus, the canonical divisors form a linear equivalence class. In particular, they are all linear equivalent. No, any two canonical divisors are linearly equivalent. And so, in particular, they have all the same degree, because the degree is invariant under. In particular, they all have the same degree. And now, and this is an important isomorphism invariant of the curve. So this, so the degree of such a canonical divisor is an important, maybe the most important isomorphism invariant of curves. Actually, normally it comes in other guises, but anyway. So it's clear that if two curves are isomorphic, then their function fields are isomorphic, and if I kind of use the isomorphism to identify them, then the multiplicities of the corresponding divisor at the corresponding point is precisely the same. So the degree of the canonical divisors will be the same. So, so this is an isomorphism invariant, and I will just formulate this, give this a definition. Namely, this is definition. So let's see the curve like this. So the genus of C is G of C, which is defined to be, so I take, it turns out if I take the degree of this KC, I can divide by 2 and add 1, and this is the genus. So there's another equivalent definition which if we have time we get to later, but I maybe doubt it. Anyway, so this is a very important number that's associated to every curve. In fact, obviously I cannot show that, but if you are over the complex numbers, then an algebraic curve is a Riemann surface, an oriented Riemann surface, and so you can write it somehow like, something, a sphere with so many handles, and the number of holes you have here is the genus. So this is, for instance, G is equal to 3. So if you have P1, according to this, looks like it's just this 2 sphere, would be G is equal to 0. So the genus is this number. But this doesn't follow obviously from this definition. I just tell you that over the complex numbers, this is the geometric meaning. So it shows you that it is an important invariant, and you can see it from this crazy differential forms. And now, so in the moment it's not clear why this should be an integer. If I have time, I will give you another way how to compute the same number, which makes this obviously an integer. But so now let me try to compute the genus in some cases. So anyway, this is the most basic invariant of a curve, which you can also see from this picture, how it looks like, you can see from this number how many holes it has. That seems really important. If you have a torus, G is equal to 1. If it's a sphere, G is equal to 0. If it's a torus with, I don't know how it's called, Rätsel or whatever it has, G is equal to 2.
How do you define a genus for a surface in R3? The number of folds, how we define it mathematically?
Well, you can define it in terms of the topology. So it's the same. If you take the second homology of this curve, so with the z coefficients, this is isomorphic to z with the 2g. Okay, so it tells you those. So it follows from the algebraic topology. Okay. So
but this also assumes there is a notion of G. What is G? Or this is a definition of G?
This is how the genus of the curve C can be topologically computed like this. So this number G of C is equal to this number of G of C. So if you take this over the complex numbers, then it looks like this. And you can kind of see this. It's not, I don't know what you did. In principle, you might be able, in small cases at least, to prove this by using the definitions, and maybe not with the, I don't know precisely what kind of methods you have, but so it's not terribly complicated. So let's now show that the genus of P1 is equal to 0. So from the definition, not with this reading length. For example, so G of P1 is equal to 0. So we just want to look at our definitions. So let x0, x1 be the homogeneous coordinates on P1, and we put x equal to x1 divided by x0, the usual coordinate on the A1, and we put z equal to x0 divided by x1, which is the coordinate on the other fine chart, u1, which obviously you can also write as 1 over x. So this is, so note that z, this is a uniformizing parameter at the point infinity, which is 0, 1. If you just look at it, this can be identified with A1, and the coordinate on it is this thing, and then therefore it will be a uniformizing parameter at 0. And in the same way, x minus a is a uniformizing parameter at the point A, by which I mean 1a in the A1. With the first, so if I take x minus a, this is a function, a uniformizing parameter has to vanish at the point, so I obtain this by subtracting a, and then it vanishes to first order, so it is a uniformizing parameter. And so we can just compute this. So therefore, let's look at the differential form dx and see what its degree is. So dx, this is the same as d of x minus a, because d of a is 0, because a is constant. And this is a uniformizing parameter, so therefore this differential form on a1, so outside the point infinity, does have neither 0 nor pole, because the coefficient is 1. No, and x minus a is uniformizing parameter. No, at all a in a1, so it follows that nu p, nu a of dx is equal to 0 for all a in a1. So we only have to worry about what happens at infinity. And that's a bit more difficult. So at infinity, so we have that our uniformizing parameter is 1 over x. So dx, you still have to take the same differential form. You want to know the degree of this differential form. This is the same as d of 1 over z. No, because x is 1 over z. So this is minus 1 over z squared dz. And dz is a uniformized parameter. So it follows that nu p, nu infinity of dz is minus 2. So we have full of order 2. And so thus the degree of dz is equal to minus 2, because it was, and so the genus is 1, is 0. Okay. So we can, in this simple case, one can compute the genus just by like this. And now I want to attempt something.
This says correspond to a sphere, the projective line?
Well, yeah, so over the complex numbers, the projective line is a sphere. I think you can, over the complex numbers, it's just C added one point at infinity, and it's really the one point compactification. But obviously, our definitions don't necessarily, I just had this picture over C. We work over an algebraically closed field, so it's not really, it doesn't have to be C. And then you cannot argue like this. The genus makes sense without these pictures. But obviously the intuition is maybe nice with such a picture. And I also like to work over C. Now, we want to show that there are also curves of other genera. And in fact, we want to compute the genus of any plane curve. Okay? That's a bit more tricky. It's in some sense a similar computation, but we really have to be a bit more careful. So I want to show, so this is the following theorem. Let C in P2 be a curve of degree D. So that means, just C the ideal of C, the homogeneous ideal, is the ideal generated by F, where F is homogeneous of degree D. And obviously, curve for us means non-singular curve, so C is non-singular. Then the genus of C, anybody guess? Well, most likely looked it up in the book. So it's this number, 1/2 D minus 1 times D minus 2. Okay, so it's a kind of somewhat interesting formula. So it's something that maybe you wouldn't find so obvious. You know, you take the zero set of such a polynomial of degree 25 in P2, and now I claim it's a Riemann surface with so and so many holes, and the number of holes is this number. So it's not so obvious. You just can compute it from the degree of the equation. Okay, so let's try. So note, so this shows if say D1 is bigger than D2 and D1, D2 is not equal to 2, 1, then then a curve of degree D1 is never isomorphic to a curve of degree D2. So this is, so in particular we now find that there are infinitely many isomorphism types of curves. Now, it actually turns out that there is a space which parameterizes curves of a given genus, and this is actually a positive dimensional space, so unless the genus is zero. By the way, one should also see this case, if D1 is, we had, I think, an exercise. Anyway, it's easy to prove that the curve, a smooth curve of degree 2, is isomorphic to P1. So that actually, in this case, the formula also says the genus should be 0, and it is isomorphic to P1. You can just, I think it might even have been an exercise once. I don't remember. I think it was, or at least something from which you could follow was an exercise. Now let's try to prove it. So we have to write down a nice differential form on this curve, and we have to be able to compute its degree. And as the answer is not totally trivial, this cannot be a completely trivial exercise. So let's write it. So we take F, our polynomial. So of degree D, which generates the ideal of C. So I write, say, large X for, so I first restrict my attention to this chart where x0 is non-zero, or if I can put x0 equal to 1. And I want to write a nice differential form there, which has neither 0 nor poles there, and then have to look what happens to it at infinity, a little bit like we did before. So x, I write x1 divided by x0, y, I write x2 divided by x0, and I write x and y for their classes in KC. No, I take these things restricted to F and look at them as elements in KC. So I write also F of xy for my polynomial F, 1, x, y. So this is just in some sense, the restriction of this polynomial to A1, where this coordinate is from 0. So note, if I take this f of, now I take the first corresponding function, small x, y, this is the 0 function. Because, this thing, f of 1, f lies in the ideal. So if I take the corresponding functions on x, it's the restriction of this f to c. And c lies in the ideal, so it vanishes there. So this is the 0 function. So therefore I can take its, because f restricted to c is the 0 function. So therefore I can take the differential of f. And as it's 0, I know that the differential is 0. So thus 0 is equal to df xy, which is equal, by what I had, to df by dx of xy dx plus df by dy. So this is 0. So I can kind of bring this, kind of separate the terms, bring them on the other side. So I find that dx by df by, so this is a round partial derivative, by dy at xy is equal to minus dy df by dx of xy. These are the same differential form. And I call this omega. And I want to compute the differential of omega. Right? So compute the divisor of omega. So now we have to be a little bit careful. So we take any point in a point in C intersected A2, which is the same as C intersected U0, so the point where the first coordinate is 1. So I take any point here. I want to look what the divisor looks down there. Then it follows, so as C is non-singular, I can remember the definition of being a non-singular point. It means that what we had called the differential of f is not 0. So that means it follows that df by dx at p is different from 0, or df by dy at p is different from 0. So one of these must be non-zero, which also kind of, so which shows that there will be no hole here. And furthermore, so if df by, which one did I want? dy is fp is non-zero, then I have to remember, so then I claim that x minus a is an element in mp minus mp squared. X minus a is a local parameter. A uniformizing parameter. So P, where obviously P is equal to A, comma B. So why is that? So if the f by dy of P is non-zero, then it follows that if I take the differential at f, of which the tangent space is the zero set, is equal to alpha x plus beta y, and this beta is this differential, so where beta is different from 0. And so the tangent space P of C is the kernel of this differential. So it's a one-dimensional vector space, so this is, what will be the kernel of this? This is the vector space generated by minus beta x plus alpha y. The one-dimensional vector space generated by this. So therefore, if I take this, so to such a tangent vector, we had associated a map which acts on MP modulo MP squared. So if I take this, how to call it, maybe delta, no? So we had identified the tangent space in the old sense with the tangent space in the new sense. The tangent space in the new sense was maps from MP modulo MP squared to K. And this was this delta. So delta of this element, so just of this vector, if I apply it to the element x minus a in NP, well, what is it? You basically take the derivative in this direction, so this will be equal to beta, different from 0. And so this means that, so this x minus a defines a non-zero element in NP mod NP squared, because this was a map from NP mod NP. This is a map from NP mod NP squared to K. If applying it to an element you don't get 0, this means this element is not in NP squared. And so it follows that x minus a is a uniformizing parameter at P equal a. Okay, so the same argument obviously, so in the same way obviously, if it's the other way around, if the derivative, so this is, we have this, and y minus b is a uniformizing parameter, and, or this, and x minus a is a uniformizing parameter. And so, therefore, so note that dx is the same as d of x minus a. So therefore, if I take dx over df by dy of p, so if df by dy of p is different from 0, then this thing is a differential form. So if I just take this at the point, so if this is not 0, then mu p of this will be equal to 0, because this is a uniform parameter and this thing does not vanish or have a, is non-zero, and okay. And in the same way, if the x of p is different from 0, then it follows that dy divided by df by dy of x1. So the mu p of that is equal to 0. Note that, so here I've just said that this doesn't vanish, this thing itself cannot have a pole there because f itself is a regular function. Okay, So this shows, thus it follows, if I take, so for all p in A2, we have that the multiplicity of omega at p is equal to 0. So this divisor of the divisor corresponding to omega can only be supported at infinity. Now we have to look what happens at infinity. You know, see, it's kind of complicated, but not very so. So let me try to see that. Where am I? Where am I? Ah, on the other side. So thus it's enough to see on the zero set of x0. So we can assume that the point 0, 0, 1 is not the point in the curve. No, it's just one point. You can move it a little bit by just translating it somehow so it doesn't pass through precisely this one point. No, it certainly has to intersect the line at infinity, but it doesn't have, you can make it not move through one point. Otherwise one changes this, so that means C is contained in U0 and U1. No? So the intersection of all, no, okay. So now I do the same thing again with the local coordinates on this, on U1. No? So let U equal to x0 divided by x1, V equal to x2 divided by x1. So they're just the coordinates on the corresponding that make this A1 into U1 into A2. So U and V, their classes in the function field of C. And then we do the same way. We do the same thing. So I write G of first U, V to be what I get from our F if I put myself in this chart. So put the this coordinate x1 equal to 1. So this is F of U1. V. And so that means, in particular, we have that if I take C intersected U1 and identify this with A2, so if I identify this with A2 in the usual way, then this will be equal to the zero set of G. No, because it's just. So, now, we are on the curve C, so if I put U, small u and v into this function will be 0. Because on U, or on C, this polynomial f is 0. So, and I take g of small u and small v, this is equal to 0. So I can take, I can use that. 0 in KC. And we have to remember, if we look at this, that note that u, the small u, which I now wiped it out, but we have that small x was x1 divided by x0, so this is 1 over x, and v, maybe I do it the other way around, so I want to rather say that x is equal to 1 over u, and y is equal to v over u. No, because this was x1 divided by x0. This was, you can see them here, so we have this equation. So therefore, if we take our, so we had our differential form, we had, so if we now look at our original df by dy and apply it to xy, what is it in these new coordinates? So this was a small f actually. This is equal to the partial derivative by f by dx2 of 1 over u v divided by u. Is it like this? Yes, because x is, this was by itself. So maybe I can do it in one more step. This is df by dy of 1, x, y. Now I put this there. This is df by the second coordinate. So here by the second coordinate of 1 over u v divided by u. And we can obviously compute this. First we just pull this out. This is so this is now this f, which was a power homogeneous. We can just multiply by the corresponding power of u to get rid of it. So this is so e power I. This thing before I take the derivative is u to the n. So 1 over u to the n f of u, 1, v, but we have to first take the derivative, so it becomes 1 over u to the n minus 1 of d by dx2 of f of this. Okay, so it's all kind of high school math, but somehow, so we do this. And so, if I write this, now I have it in the terms of the g. So g are the coordinates that we have here. So we have this is equal to d dg by dv of u v times 1 over u to the n minus 1. So therefore our omega we can write in terms of this, because we know what this thing is. This was there before in the omega, and it is equal to this. Omega, which is equal to dx over df by dy of xy, is in this chart equal to d of 1 over u divided by this thing. 1 over u to the n minus 1 dg by dv of uv. That's right. Okay. So what? This is equal to minus what? From?
Small g.
Yeah, this was maybe a small g and this was a small f. So this is minus, what is it? U to the n minus 3 du by dg by dv. Okay, and in the same way, obviously it works if we in the other chart in the same way. We can also instead do things with respect, we can take df by dx and then do that in terms of the other one. So one shows that omega is also equal to u to the n minus 3 dv divided by dg by dv of u. Okay? So you do the same computation with the other expression, then you get this. So what we see here, and we have the same story as before. So we have that C is smooth, and the u and v are the local coordinates there, are the coordinates on A2. So we can apply the same thing as before. Either this derivative is non-zero, and then the other coordinate, the u, is a local parameter, or the other way around. So this was actually not v, but u. So as before, for all points p in say equal to A1b in C intercept U1, we have dg by du at p is non-zero, and v minus p is a local parameter at p, not v minus p, v minus b, or dg by dv at p is non-zero, and u minus a is a local parameter. And uniformizing was the word I used. At p. So we have all of these. So we can precisely see if this is non-zero, and it also is anyway a regular function, so also no pole, we can precisely see what the order of pole is. So thus, where is it? Now I'm almost done. Thus, for all p, in C intersected the zero set of x0, which is when we're here, we have that the multiplicity at p of omega is equal to the multiplicity at p of this, of this thing, of u to the n minus 3. And we had assumed, so u is just a restriction of the coordinate function x0 to our chart, and our curve does not have any point on the intersection of the at infinity of this of this line. So this is the same as nu p of x0 to the n minus 3. So where x0 is the coordinate function, not just the restriction to the chart of x0 is u. And if I take the intersection, if I, when we are on the curve and x0 is 0, and also so there's no point on this line of u at infinity which lies on the curve, because that point would be this one. So therefore it is the same as this, and we know that therefore the divisor of omega is the same as the divisor of x0 to the n minus 3. we know that the degree of the divisor of the polynomial, so I wrote here n. So I hope that didn't confuse you. N and d is the same, no? So I had a curve of degree d, and then somewhere in between it became n, namely here. Was this clear, or were you just pretending you understood? No, I mean, just to go back, no, you have this curve of degree. Let me say the degree is d. Then when you look at this, you know, if you replace the variables by 1 over u and b over u, then the degree of it comes out. And so this number should have been, with the correct notation, should have been d minus 1. And then it would follow through to this. You get the d minus 1, you get d minus 3. And so you go on and you get here d minus 3. So I have now the divisor of omega is the divisor of x0 to the d minus 3. And we know that the degree of a polynomial, of the divisor of a polynomial of degree of some degree is d, the degree of the curve, times the degree of the polynomial. So it follows thus the degree of the divisor of omega is equal to the degree of c times d minus 3, so d times d minus 3. And then, you know, if one applies the formula that g of c is equal to the degree of the divisor of omega half plus 1, we get g of c is equal to 1 half d minus 1 times d minus 2. Okay, so that took a little bit longer than I thought, and was maybe also. Anyway, so this is this thing. So maybe I. So in the same way, this is an easy exercise. If you have understood this proof, you can certainly prove that. So modify the proof to show if C in P1 times P1 is a curve of by degree A comma B, so the idea of the curve is generated by one polynomial of by degree AB, then it follows the genus of C is equal to A minus 1 times P minus 1. And so in particular, you can see that every positive integer occurs as a genus of a curve. Yeah, now I don't know. Normally I would now, so I wanted to also say something about the Van Roth theorem and the elliptic curves, but maybe that's, there's not so much point in doing that. So I can just briefly say what the next things would be without actually doing it. So the Riemann-Roch theorem is a formula for finding the dimension of these spaces L of D, where D is a divisor. In fact, I maybe will still write it down so you can see how it all fits. So, so for one thing, I can start by immediately changing my definition of the genus. I can also, I will see, I say the genus of the curve C is supposed to be, now as another definition, to be L of the canonical divisor. Then obviously we'll have to see that's the same definition as before. Now we'll see in a moment. So then one has this theorem that, so this is the Riemann-Roch theorem. So Riemann is the usual Riemann of Riemann surfaces, and Roch is his, I think, PhD student. And so let D be a divisor on C. Then this number, L of D, if you remember, this was the space of rational functions such that the divisor of the rational function plus D is effective. So then L of D, and so this was the space, and small L of D is equal to the dimension of that. So if I take L of D, one would like a formula for L of D. Now that we can't, so one has something like this. This is equal to the degree of D plus 1 minus the genus of C. But there's an error term, and this is the degree of Kc minus D. Okay, so L of D is the dimension of what I call L of D, and L of D was the set of all F in Kc, well, I have to add 0, such that the divisor of F plus D is effective. Okay, so this is a vector space, and anyway, so the dimension of this vector space is this, and this, for many reasons, well, one likes to do this thing, also because one uses these spaces to construct morphisms. Anyway, so there's this. So the original theorem by Riemann was, so the corollary is rather obvious. This is was the original result by Riemann, that if I take L of D, this is bigger equal to the degree of D plus 1 minus G of C. So this is what Riemann proved, and then his student Roch found what the error term is. Okay. And I should say, so this thing has very far-reaching generalization. So you can do something, you can generalize this for varieties of arbitrary dimension, and for D you can take, you can replace this L of D by sections of any vector bundles. This is the so-called Hirzebruch-Riemann-Roch theorem. Hirzebruch was my advisor, so that was what made him famous. And further, you can view these things in the complex setting as spaces of solutions to certain partial differential equations. And then it becomes a statement about dimensions of, about the index of certain differential operators on certain manifolds. And then it becomes the Atiyah-Singer index theorem, which, for which, which is one which some people say was, I mean, it depends on who says it. Some people say it's the most important theorem of the 20th century or something. But anyway, it's certainly a big theorem. So Atiyah got the Fields Medal for it, and both of them the Abel Prize, so certainly give them some fame. So this all is somehow, this kind of the baby version of all that is this theorem. Okay. Unfortunately, so I haven't developed the tools to do this. The natural language would be cohomology. There are also elementary proofs, but they're a little bit intricate, and find it in Fulton's book, but it's somehow a little bit arbitrary to avoid cohomology. Anyway, so that's this. And then, another corollary, maybe as I talked about this, is that the, what I gave, so that my two definitions of genus are the same. I have now the genus before was this, and now I've given you another definition. Obviously, this only makes sense if they are equal, and this must be written somewhere. Yeah, so the degree of the canonical divisor of the curve C is equal to 2g of C minus 2. So for this we apply the Riemann-Roch formula for D equal Kc. So apply Riemann-Roch to Kc. So what do we get? We just put it in. L of Kc minus L of Kc minus Kc. So L of the zero divisor is equal to the degree of Kc, which in the moment now we don't know. We want to show that number, plus 1 minus g of c. So so what is L of the zero divisors, which are all functions, all rational functions, whose divisor is effective. So that means all rational functions without poles. We know that rational functions always have poles unless they are constants. So these are precisely the constants. So that means this number is 1. Because if I take L of 0, this is equal to K. It's a constant function. And so if we bring it on the other side, we get the statement, namely, we know that L of Kc, by our definition, this is equal, so L of Kc is equal to the genus of C. So if we put it together, we indeed get the degree of Kc is equal to twice the genus of C minus 2. And this is, the previous form. Yeah, maybe I mean, now I could also tell you about elliptic curves, but maybe I will not. So one can quite easily from this deduce that there's a bijection. So between, maybe I will just say it in this. So this actually, it's easy to check. I call it exercise. So we choose, so let C be a curve of genus 1. And choose any point, which I call O, to be confused with 0, because somehow it will be the 0 element, any point in C. Then now I have to look at the statement quickly. Then, if I take the map epsilon from the curve C to peak 0 of C, which sends a point to P minus this O as a divisor, this is a bijection. So in other words, I can, so somehow you can, so no two of these will be linear equivalent, but every divisor of degree 0 is linear equivalent to this in a unique way. And this you can easily deduce from the Riemann-Roch theorem if you assume that the curve has genus 1. And so this means, in particular, you can also, so for one thing that's anyway nice, so because this is in some sense, this is an example of, we have in some sense now described a moduli space. So we look at the space of all divisors modular linear equivalents of degree 0 on C, and this is naturally bijective to the curve itself. So we have kind of, so moduli space is in algebraic geometry is a space which parameterizes some nice geometric objects on our space. We have found one such moduli space, which is good. And in addition, we can also use this to deduce that C itself is in a natural way a group. If we choose, we can use this by just saying that we decide that this map is a bijection. We define a group structure on C such that this is an isomorphism of groups by just saying that P plus Q is equal to whatever you so okay, so just whatever you get here. And then finally one gets another exercise. So with this definition, so if so assume now, I know if I have a cubic in P2, this is a curve of genus 1. So let's assume we take let C be the zero set of, say, Z times y squared minus x to the 3 plus ax z squared plus z squared, z to the third. So it's a cubic. The coordinates now I call a, b, and z. So one has to think that my coordinates are somehow z, x, and y. So this is kind of like 0. So we look at this thing and assume it's non-singular. No, so which actually amounts to the thing that this polynomial has no multiple roots. And then one can describe the structure as follows. So if I look at, for instance, the real points, it will somehow look like this, somehow symmetric. So here is the kind of the y equals 0 axis. And so if I take a point P and a point, maybe I could, so if this is my point P, this is the point Q, then how does one get the sum? You take the line connecting these two. This will intersect in the third point because the degree of this divisor given by a polynomial of degree 1, linear polynomial, is 3. Then I can reflect it here. So this is a point I call R. Sorry, this is symmetric. I go down here, and this point will be P plus Q. And this point actually will be minus P plus Q. Anyway, so this is a geometric description of the group structure, which one obtains in this way.
But this is under assumptions that O is choosing to be the void at infinity, right?
Yeah, well, yeah. So, yes, so that I forgot to say. So obviously obviously it depends on the choice of O. So O is 0.001. And this then will become the neutral element of this. Okay, so this is just an example. This follows, so this statement easily follows from the Riemann-Roch theorem, and then this is quite elementary. Just, you know that the line has degree, intersects in 3 points. Anyway, I didn't have the time to do this, but you can do these 3 exercises then.
Big note is a group, right?
What?
Big note is Picard group, right?
Yeah, Picard, that I showed.
But what is a group?
What?
What is a group?
Oh, this is just, it's divisors, no? So a divisor is just...
what is a group?
What do you mean, what's a group? An Abelian group. What do you mean, what's a group?
The definition.
What? Okay, so because it's so long ago that we talked about it, or was it? Anyway, it's an Abelian group, and what?
It was supposed to be a joke.
Yeah, okay. Yeah, so okay. Now I have tortured you enough, I think. So yeah. So thank you for your attention and your patience. And yeah,